Hello, Energy Fellows. Welcome to Windwin, Rhode Island's workshop on blades, turbine blades, and it's an activity that will engage students in building model blades and testing them using both the engineering design algorithm and scientific inquiry. Okay. We are actually modeling this off of a document put out by the Kidwin organization. Let me get this right. Which blades are best? Okay. So, how will this all be done? Well, we'll set up over at the Bay campus about 8 o'clock in the morning. We'll set up some workstations where students will actually build the blades. At those workstations, we'll have kits of materials. Each team will get a kit of materials. They'll get some tools, some very simple tools, glue gun, tape, some gloves, clips, okay? And they'll build something that looks like this. Okay, there's a sample of blades. They'll go through a predetermined set of tests to evaluate their design. Their designs will be based on one particular variable about the blades. We will have probably, I would say probably 6 teams of 4 students each, maybe up to 10 teams of 4 students each. So students will build the blades. They will test the blades using a test setup, which I'll show you later. This is the unit that they put their blades on. Okay, and it's called a standard Kidwin configuration. I'll show you more about testing in a few minutes. Okay, so there'll be a specific set of a specific variable each team will test for. They'll have about an hour and a half to build and test, and then they will, under the guidance of their mentor or engineering fellow, they will come up with a report, and they will put the data on a chart, put the chart on the wall, and then they'll have 5 minutes or so to talk about what they did and what they found. And hopefully we'll come up with what blade is best from all the different designs. So what is the job of the mentor or engineering fellow? Well, we're going to have students from schools throughout Rhode Island. We're going to have students of different ability levels. We're going to have students that understand about wind power and other students that have never even thought about how wind is converted into electrical energy. So you as a mentor will be the guiding voice as to how they go about deciding to build their blade, how they decide to put it together, and what shape it should take, because that depends on their particular assignment. Okay, then they'll probably need some help setting up in the test tunnel, and then they'll need some help analyzing the data. There will be a little bit of math involved in calculating the turn speed ratio to see if in fact they built a blade that actually exhibits some lift. It's an exciting activity. I've done it many times with adults and other students, and you should find it very very rewarding to help some of these students through some technically difficult components of this particular assignment. Okay. As you can see, these blades, here's the simplest of all the systems, right? And so we just see that the cardboard blade is glued on a dowel, and there's a hub that just fits on that generator. It just snaps on. Okay. Okay. So we will have to set up everything early in the morning. We'll probably get there at 8 o'clock. Students will come in about 8:30. They'll be in another room where they'll see a presentation. Presentation will be put on by industry officials, and it probably will be a good presentation to listen to. We could use that time also to make sure we get all the benches in order and all the cords taped down and equipment put at each workstation. So then there'll be a little discussion about the engineering design cycle and how scientists collect data. Okay. Then they'll be given the task to go to their workstation with you and to begin their planning as to how they're going to do their particular assignment. Then they'll start working on it. Then you'll go with them over to the test wind tunnel. They'll test it. If there's any failure, they may have to go back and redo something. There'll be certain variables they'll have to test for depending on their particular type of assignment. They may be changing pitch. They may be changing the number of blades. They may be changing blade shape. These are defined variables that each team will be given before they start their testing, okay? Before they actually start their build and design. And so you'll sit with them and then go back to the desk and say, what does this mean? How do we evaluate the data and put it in a format that other people can understand? We'll put it on a big post-it on the wall. All the team's data will be on the wall. We'll look at them all. And again, each team will have 5 minutes to say a little bit about what they did and how well it worked. Then the students will leave about 1:30. We will get together, clean up the room, and then have a brief debriefing session amongst ourselves. Congratulate ourselves for the good work we did, and that's the day. Thank you for your time. Yeah, this, if you look at the setup here, you've got a generator with an 8:1 gear ratio. So the blades fit into this hub. The hub just has a wing nut on it. You push the blades in, and then you just tighten up the wing nut. Okay. I got a little piece of tape here, reflective tape, so I can measure the RPMs of the blades. This is the only way you can really tell if the blades are aerodynamic or not, is to compare the RPMs of the blades to the wind speed. Okay, and so if your meters per second of the tip of the blade is faster than the meters per second of the wind that's providing the force, then you have a airfoil that actually is lifting, and this is pretty much the basic fact that why wind power is so usable, is the fact that we can spin these blades much faster than the actual wind speed and catch as much kinetic energy as we can. Okay, so that's that. On the back side, you'll see this little nub here, and this nub just plugs in like this, okay, and kind of pushing it real hard, and then there's usually a screw that you tighten with a screwdriver or by hand, and that's enough to hold the blades in. Okay, and so you got to turn that so. Okay. Now the couple of instruments we'll use an anemometer to tell the wind speed. Okay, and again you can see our setup here, right? The distance from here to here remains fixed for all our experiments. It's usually about 2 feet, and this particular fan will give us about 3.8 meters per second, which is good enough just to start to see the aerodynamic effects of a good blade. Okay, so the other instruments we'll need, this is a protractor. It's probably not the one you're most familiar with, but it's a large protractor, and it has a digital readout, so you can actually measure the angle which you position the blade at. So really a vertical blade is at 0 degrees, and anything beyond that is whatever, minus or plus, minus. So if you go to 100 degrees, you're at 10 degrees blade angle. Okay. So one of the variables we will set will be the blade angle. That's important to know. And if you look at these blades, you'll see there is a certain amount of blade angle set there. Right. So this is the root of the blade. Okay. And this is usually you can set the blade angle here. But there's also another blade angle here at the tip of the blade. Now these blades are straight. Commercial blades are not straight. They have a twist to them, and they're pretty much almost at 0 degrees at the tip, usually about 15 at the root. Okay. But again, we'll give the students an assignment. We'll tell them what angle to set here. Okay. And all blades have to be at the same angle. The other instrument we'll use will be the multimeter. Okay, and these are all DC voltage. Again, this is not really difficult to do. Okay, so just connecting up the generator to the meter will give us the reading. Okay, so this happens to be set right now at it's on DC voltage. We'll have different multimeters. We'll go through the different multimeters, so you'll be familiar with it. Okay. So the setup then is with the turbine fixed distance from the blade, which we'll put lines on the floor so everybody gets the same distance, and we'll set the fan for high, which will give us our speed. Okay. The other measurement we'll do is we'll check for the revolution, the speed of revolution of the blades, and there's a little bit of reflective tape down here. Okay, that's what that happens. So these blade angles have been set. This is a 5-bladed setup. That's one of the situations. I push the blade on and I tighten the screw. You might need a screwdriver or an Allen wrench to do this. Okay, so this is the amount of time it takes to set up for the test. So now our meter will connect up to the leads from the generator. Okay, and again, this will be standard for every generator, every setup. Okay, and right, so if you turn it, you should see some voltage. If you don't, you're probably on AC. Let me just, no, this is DC, so let me try it again. Oh, one of my leads came off. Okay. Okay, here we go. Okay, so we can see the voltage. Okay, so get my tower back on the line, turn on the fan. Give the turbine some time to get up to speed. Okay, I figure at least a minute. Okay, record the number. Don't be concerned about the last digit. Okay. Turn off the fan. Okay, so that's the voltage reading. Now the other reading we would want is the RPMs, and that's some of the tachometer, which is this instrument. And this instrument has there's a test button right here. And when you push the test button, you shoot, whoops. Okay, so it will project a beam. You can't see, I'll bring the camera over here. You see that red beam, and that has to hit the tape. So this one you have to literally do by hand. Okay, and so the tape's at the tip of the blade. So I'm looking at the tip of the blade right there, see it? And there's my reading. So looks like we're measuring 189 RPMs. Okay, so we convert RPMs to RP seconds, revolutions per second. Okay, figure the circumference of the blades and use that to calculate the rotational velocity of the blade. I'll give you an equation for that. Okay. That's it. That's the test equipment. That's the testing procedure. The only other thing I've got to say is that safety is always a concern. We should have safety glasses available for students, and we have gloves if anybody is interested in wearing gloves while they're working. But it should go pretty smooth, and students enjoy doing this. It's a lot of fun, and hopefully they learn a little bit about wind power and how wind is converted to electrical energy. Okay? All right, I'll be online for anybody that wants to get in touch with me. This is Mike Rinaldi from Windwin, Rhode Island.